Hello everyone and welcome to my presentation on continuous fiber additive manufacturing in the automotive industry. I'm Ryan O'Quinn and I'm happy to be presenting this exciting topic to you today as part of ME 6560. To give you an overview of what this presentation will cover, we'll start with a crash course in continuous fiber composites, what they are, their applications in the automotive industry, and the things to consider when we manufacture them. With that, we'll be prepared to dive into additive manufacturing of continuous fiber composites. We'll go through an overview of the processes and on-the-market options available, and then we'll cover the performance that can be achieved through these techniques. Then we'll conclude and take any questions that you have. So what are continuous fiber composites? Well, a composite combines two or more materials where each retains its unique identity and properties. And when we're talking about fiber reinforced composites, those combine fibers in a polymer matrix, which could be either a thermoplastic or a thermoset matrix. The fibers could be glass, carbon, aramid, natural, or others. And when we're talking composites in general, they can come in either chopped or continuous form. Chopped provides modest increases in strength and stiffness, but today we're going to be focusing on continuous fibers because they can provide much greater increases in strength and stiffness, and that's demonstrated if you look at the little GIF over here. You know, the one on the left here is continuous fiber. You can see it deflects much less. Chopped fiber still holds but deflects significantly, and the no fiber doesn't hold at all. So continuous fibers can come in the form of woven fabrics, non-woven mats, unidirectional tape, and roving or tow as pictured up in the top right there. So continuous fiber composites applications in automotive are primarily centered around lightweighting. So the idea is if you can reduce the weight of a vehicle, then you can improve its fuel economy. And continuous fiber composites are well suited for this because they can offer greater specific strength than aluminum, steel, and other materials. Then secondarily, as an added bonus, composite designs often enable part consolidation. And an example of continuous fiber composites in automotive is a joint Department of Energy, Clemson, and Honda project to design and manufacture an ultra lightweight thermoplastic composite door. Here, 45% reduction in the total door weight was achieved, and also around 45% reduction in part count was achieved through continuous composite design. When we manufacture continuous fiber composites, we have a few goals in mind. And the first two go hand in hand. One is to obtain good fiber matrix adhesion, and two is to minimize voids through consolidation. What these two goals are getting at is we want our fiber and matrix to combine such that when they're loaded, they behave as one. And we do this by having our matrix fully penetrate and impregnate all of our fibers and eliminate these voids. And this is done through the application of pressure and sometimes heat. Another goal is to align our fibers with our loading, because fibers only have strength and tension. Another goal in manufacturing is to eliminate fiber discontinuities. So if we look at the image on the right here, we can see how hints can be taken from nature, wherein trees have continuous fibers that wrap around the curves in their branches like this. And this is actually a much stronger and more efficient design than what traditional composites often leave us with, which are these discontinuous joints. Another goal is to minimize fiber attrition. We don't want to tear up our fibers. And finally, we want to minimize tooling and processing costs. An example of some challenges in traditional composites manufacturing is back with this ultra lightweight door design. The sharp curves in the design actually cause drapability issues when laying up the woven fiber fabric that was used for the composite, and so the design actually had to be adjusted to accommodate this. Now that you know a bit more about continuous fiber composites and what we're trying to do when we manufacture them, we can dive into additive manufacturing technologies that have been used with continuous fibers. So the first is FDM, fused deposition modeling, which essentially takes a roving or fiber tow and extrudes that with our matrix material and then fuses that into our part. Next process is sheet lamination, which is similar to FDM, only instead of roving or tow, it's taking a whole fiber sheet, such as woven fabric, and laminating that layer on top of each other. The next process is photopolymeric processes, where it's important to note that carbon fibers are actually opaque to UV light and can cause challenges by blocking curing. Another process is Lita 3D printing, which is a bit unique. It drives a thermal gradient across fibers, and in doing so, it drives this wicking phenomenon that pulls this thermoset resin across the fibers and essentially simultaneously infuses the fibers and then cures that matrix as it's pulling the thermoset across. The final process is directed energy deposition, which is essentially used in combination with FDM or sheet lamination, just as a means to improve the bonding between layers here and that the consolidation that's occurring there. So overall, FDM is what has primarily been used and commercialized. And the final thing that's important to note with these additive processes is typically specialized design and slicing software is required to define fiber placement. But the good news is, because we can define and control that fiber placement so precisely, it actually makes it very good for coupling with topology optimization to get really optimized fiber layouts. Next, we'll take a look at the on-the-market options for continuous fiber additive manufacturing and the companies involved in the space. So you can see that all of these companies employ some form of FDM process, and it's only a question of how they combine their matrix and fiber, whether they have dry fiber or whether they use prepreg, or whether they do some form of inline impregnation or combining the matrix and fiber in the hot end, or whether they do some sort of in situ consolidation. So those are the technologies used, and to give you an idea of the scale each of these companies are aiming at, this graph over here shows the parts per year they're aiming at, and also the print volume that they can achieve with their processes. And finally, of the 13 companies surveyed, 4 identified automotive or transportation as a top targeted market. And before we leave, just to spotlight 2 companies here. Continuous Composites uses a pretty interesting process where they actually impregnate their fiber tow with a photopolymeric resin and then cure it by shining the UV light on it as soon as it comes out the nozzle, and so they're able to print in free space like that. And then over on the right we have Markforged, which is the established name in the continuous fiber additive space. They have their X7 industrial printer, their Mark II desktop printer, and also their Eiger software platform, where you lay out your fibers and your part and slice it. So what sort of performance can we expect from continuous fiber additive manufacturing and the parts that result from it? Well, the first benefit of additive techniques is that we can get much better control over the fiber orientation and density than in traditional processes, so we can optimize that fiber layout much more. Another benefit is that there's the potential for directly producing continuous fiber layouts in 3-dimensional space. You can see here, this is from the Lita technique, how they're going a bit 3D. And then you also saw on the last page with the continuous composites technique, how they were able to print in free space. So potentially you can not be limited to a 2D plane with your fiber layout. You can have more complex layouts. Another benefit is easier embedded components than with traditional processes. You can embed electronics or sensors, what have you. Now, onto the downsides. Achieving complete fiber impregnation is critical, and the results differ by the additive process. So again, this is what we're talking about with that impregnation. But in general, additive processes have higher porosity compared to traditional processes, which is bad. Another bad thing is when we're using these FDM processes for the continuous fiber, you still have the standard FDM challenges that are the weak interfacial bonds and voids between neighboring beads and layers. But as we noted before, that coupled energy or coupling the energy deposition with FDM can improve that bonding. This is just another figure demonstrating that. And so finally, overall, we see lesser mechanical performance if we have an identically configured additive composite and traditional composite. But the idea is additive enables you to better optimize your design than traditional composites, even though you can't quite get the quality of manufacturing in some respects. And then the final issue is the time, cost, and scalability concerns associated with continuous fiber additive. So before we wrap up here, I wanted to highlight this one company's process they call additive molding, which is sort of a hybrid between continuous fiber 3D printing and the traditional automated fiber placement technique. So essentially what they do in this process is they shape, but don't necessarily consolidate these fiber preforms, and then they assemble them and compression mold them to achieve, their final finished part here. And the entire idea behind this whole process is, by combining these techniques, they're able to achieve, mass manufacturability. Much more. And so some examples here, you see this part they made for a drone company, where they actually consolidated 17 parts into this one part. And you can see how they have both glass and carbon fiber because they have some RF radio signals that need to pass through there, and carbon fiber would not allow that. Then here you can see their little concept of how they could use their additive molding for a vehicle chassis. To summarize, continuous fiber additive manufacturing is an up-and-coming field with many companies establishing themselves. It's useful in the automotive industry for lightweighting and consolidating in-use parts, and also for fabricating tooling for automotive manufacturers. Continuous fiber additive offers more control over fiber layout and increased design freedom compared to traditional processes. But it has challenges in obtaining mechanical properties comparable to those traditional processes. Finally, automotive's long development cycle and established manufacturing and supply chain make implementation of composites challenging. But these continuous fiber additive companies are establishing themselves and making inroads in the industries where they can, so that hopefully they're setting up the long-term case for implementation in the automotive field. So with that, I'll conclude and show you my references here. Thank you for attending, and I'll answer any questions that you have.